Hello there, and welcome back to Thermal Live. I hope you're enjoying these sessions as much as I am. In this next session, we're going to look at AI-ready thermoelectric solutions for data center thermal management. We'll explore how Peltier coolers can complement conventional cooling in data centers to beat the heat from next-generation AI infrastructure. We've got two presenters with us from Sheetak. Brandon Noska is the Director of Application Engineering and has over 20 years of experience in thermal management engineering solutions that use both traditional and advanced cooling technologies. And joining him is Sean Gamarose. He's the head of marketing at Sheetak, and he's a seasoned marketing executive with experience in B2B technology and electronics manufacturing. And of course, Sheetak specializes in developing advanced thermoelectric technology for a new generation of cooling and heating systems. And if you guys have a question for Brandon and Sean as they're presenting, please ask it in the Q&A tab to the right of the chat. Now, if you'll please help me welcome Brandon and Sean to Thermal Live. Guys, thanks for being here with us today.
Yeah, thank you so much for having us. We're looking forward to it.
Great, it's all yours.
Appreciate that.
All right. So yeah, thank you everybody for joining today. We're going to be talking about some AI-ready thermoelectric solutions for data center thermal management. We already did the bios. So just a quick agenda. I'll do a brief about Sheetak, give a little bit more color to who we are as a business. Then we'll dive into the problem statement or the challenge that many of us are facing on the data center thermal management side. After that, we will go into some high-level fundamentals about thermoelectric cooling, the science behind it, and how people are leveraging this technology in today's world. Then we're going to go into solution statements for some of the problems that we are noticing on the data center front. Last, we'll talk a little bit about some of our thermoelectric solutions that can help in some of these areas. So a 10,000-foot view of Sheetak. We were founded in 2012. We are headquartered in Austin, Texas, and that is where we do all in-house design, engineering, and manufacturing. Everything we manufacture is done, like I said, in-house at our Austin-based facilities. One of our claims to fame is rapid prototyping, which is a challenge in today's world with global supply chains and things like that. So one thing we really help customers with when they're designing and implementing new thermal management solutions is a rapid turnaround time on some of their prototype designs. We carry over 25 different design patents, which is leveraged in our TEC and TEG solutions. So I think it's important to also note that we are not just thermoelectric coolers. We also do energy harvesting technology and modules. We do test and measurement equipment, and we also assist customers with simulations, design, characterizations of their own thermal management systems. So with that, let's dive into the challenge that people are facing with AI infrastructure today. So I think everybody has been sitting in on these presentations and is keenly aware that power densities are increasing rapidly in AI clusters. Chips are, roughly 400 watts to 800 watts per single chip. That's increasing. We see directions going 1,000 watts plus per package in data center server racks. Localized hotspots within chips are exceeding 100 watts per centimeter squared. We're also noticing exponential growth in optical components as we introduce hundreds of thousands, even close to 1 million optical transceiver interconnects in a single AI cluster. The amount of heat that that's generating is also growing exponentially. So some of the information that we will be talking about in today's presentation will help address some of these challenges that we're facing. Also, as Curtis mentioned, in the document section, we have a white paper that all of you guys can download. A lot of the information that we will be presenting today is derived from a recent publication that we produced. So please feel free to download that as well. So common limitations of traditional cooling methods. I think we're all keenly aware of, air cooling, liquid cooling. There's been a lot of really, really good information in this year's Thermal Live about both of these technologies. And each one of them by themselves has strengths and weaknesses. And what we aim to present today is not the elimination of air cooling and not the elimination of liquid cooling, but really a hybrid approach that companies can take to address specific applications within data centers. So I just want to make sure everybody's aware, we're not talking about the elimination of either of these. We're talking about complementing both of these conventional methods within a data center thermal management structure. So where can TECs fit in data centers today? Where we are going to be spending this presentation, we'll be talking about on the pluggable side, optical transceivers and interconnects. There's also emerging technology called co-packaged optics. We will be talking in detail about how TECs can complement a co-packaged optic design. We'll also look at direct chip cooling and hybrid boosting cooling solutions that Brandon will go over in a little bit more detail. And before we dive into each one of these topics, Brandon will give a little primer about thermoelectric technology and how it's benefiting the data center world. Brandon?
All right, thanks, Sean. Thank you for the introduction, and thanks for everyone for joining us today at Thermal Live. Yeah, so as Sean mentioned, we'll kind of go through an introduction of thermoelectrics, also known as Peltier cooling, and then talk about some of those key application spaces where thermoelectrics are currently being applied and where they could potentially be applied, in the future as AI chips continue to get more dense and the cooling challenges continue to evolve. So with thermoelectrics, just a quick little overview here. They're solid state devices. There's no moving parts. I like to think of them as kind of like a solid state heat pump, because basically heat moves from one side to the other when you apply electrical current through it. And I'll get into a little more detail in some slides after this. But the main advantages are they're compact. They can be very precise in controlling temperature. We're showing 0.1 degrees C here. In some cases, that can be even 0.01 or even more in terms of precision. They're flexible and modular in that you can scale these down to small form factors and large form factors and into arrays. And they can both heat and cool, so they're reversible. So the same device can cool something and reversing the current while also putting in heating mode, where you can stabilize the temperature and control the temperature at a very precise operating point. And then lastly, they have a very fast response time. The thermal mass of the device itself is very, very low, so they respond very quickly to changes in current. We like to call this our fire to ice slide because, as Sean mentioned, thermoelectrics can also be used to harness temperature differences and create energy. So on the left-hand side, we're showing a TEC device or a Peltier device in generation mode. Commonly, we call that a thermoelectric generator. And in this mode, you're leveraging temperature differences from, waste heat from machinery, pipes and industrial plants, or just ambient energy around, and converting that into usable voltage and power to either control a sensor or control some other device, or at least act as a battery of sorts that's generated from the ambient temperature differences around the device itself. On the right hand side, we're showing it in refrigeration mode, and that's primarily what we're going to be talking about today. But when you run an electrical current through the device, because of the Peltier effect, will actually act as a heat pump. So one side gets cold, one side gets hot, and it'll actually move heat from one side to the other at various temperature differences. And it's one of the only technologies in the market that can be used in this way, and it's the only one that's solid state and with no moving parts. So for the rest of the presentation, we'll be primarily talking about refrigeration mode, but if anyone has any questions on energy harvesting, feel free to contact us either after the presentation or as part of the Q&A session at the end. So diving a little bit deeper into the thermoelectric devices, on the left is shown a typical single stage thermoelectric device, and they're simple in construction. They usually consist of a top substrate and a bottom substrate, and those substrates are typically ceramics. The most common is alumina, so Al2O3, but ALN can also be used. There's also availability of metal substrates and other variants out there. The most common is alumina. And then sandwiched between those two substrates are the Peltier elements. We call them semiconductor legs. They're also known as pellets or elements in the industry. And essentially, those are little cubes of bismuth telluride, which is the most common thermoelectric material used in electronics cooling applications and in cooling. The bismuth telluride elements, one's p-doped and one's n-doped, and a pair of those is known as a junction or a couple. And basically, these devices consist of a repeated array of these junctions or these couples, typically in square or rectangular form factors, all wired electrically in series. And as the current flows through the devices, this Peltier effect takes place. One side gets hot, one side gets cold, and heat's pumped through it. On the inside of the ceramics are the copper traces that allows the electrical input. So usually these things have wires on them, or there's some sort of connection point to connect to your power source or your power supply, and that's what drives the current through the device. And so these ceramic substrates are basically like a ceramic electronic circuit. So on the one side, it's typically just bare ceramic, but those can also be metallized if you need them to be soldered or epoxied with certain epoxy that requires a, say, like a gold finish and such. So the elements themselves, if you kind of zoom in on the right-hand side, they're typically cubes, and these are on the millimeter scale. The main geometric factors are the cross-sectional area and the length of the element. So that's the length that the current and the heat passes through, and then the cross-sectional area is the area at which the current and the heat that you're pumping is passed through. And really, the main performance of the device is driven by kind of two factors. One, the material properties. So the equations on the bottom right-hand corner are the electrical resistance, the thermal conductance, and then the thermoelectric figure of merit called Z. And the electrical resistance is primarily controlled by this geometric factor L over A, so the length over the cross-sectional area, and then also by the electrical conductivity, so how well a current will flow through the element. And on the right-hand side, the conductance is dominated by the thermal conductivity of the material, and then again, the cross-sectional area at which that heat is being passed through, and then the length of the thermoelectric element. So you kind of see the inverse of this geometric factor, kind of A over L here. And then N is the number of junctions or the number of couples that the device has. And then the figure of merit is kind of a measure of how well a thermoelectric device will perform in terms of its delta T max and its cooling power. And you can see the main component on top is the Seebeck coefficient, and it's a squared function of that parameter, and then the electrical conductivity, and then over the thermal conductivity. So what makes a good thermoelectric device is something that has high Seebeck, high electrical conductivity, and very low thermal conductivity. That makes a really good thermoelectric material. Some other equations that are important in analyzing devices are, in addition to just the material figure of merit, another way of casting that figure of merit is ZT, and T is the absolute temperature at which that metric is kind of defined at. Sometimes you'll see T bar because it's the average temperature between hot and cold, and sometimes you see T hot. So it's kind of the reference temperature that the material properties and the performance of the device is specified at. But again, you kind of see the same base equation, the thermal conductivity, electrical conductivity times Seebeck squared over the thermal conductivity, and then times T, where T is the absolute value. And the thermoelectric materials will vary over temperature, specifically the Seebeck value and the electrical conductivity. So typically, bismuth telluride, as I mentioned before, is used in electronics cooling because it operates it's the most efficient material for operating in the temperature ranges that we're talking about. Typically 100 C or lower, down to say 0 C. And there are other materials that are out there that are typically, for higher temperature operation and temperature, for energy harvesting and power generation and such. But for bismuth telluride is commonly used at the room temperature. Kind of these temperatures, electronics cooling is required. And the ZT value for kind of a standard, module in the market is kind of on the order of 0.7 to 0.8. So that's kind of a reference of what you would see in the market for various thermoelectric materials. Another important equation is the COP, this coefficient of performance, and that is basically how much the device is cooling, so your Q that the cold side is absorbing, and then over the electrical input that the thermoelectric is required to power to generate that delta T and to actively cool that Q. And in most cases, for low temperature differences, the COP can be high, it can be above 1. But for a lot of cases, when you need temperature differences on the order of 30, 40, 50 degrees temperature difference across the device, the COP is going to be less than 1. And so what that means is you're going to be putting more energy into the device than you are cooling. And that, is a trade-off that you make when you're analyzing systems and analyzing different, technologies that you have for your application. But there are cases where we can design for what we call COP max. And although that may not be the COP greater than 1, for every device and for every kind of application, there is an operating condition where we can kind of maximize that COP. So we can basically make it the most efficient for that particular operating point. And I'll talk a little bit more about that here shortly. And in terms of the cooling equations, these are the base equations that define the cooling going through a Peltier device. So you kind of see the cold side loading here, which is kind of the Peltier effect minus the losses through the system, the I²R losses, and then the thermal conductance losses through the device. And then here's what the hot side will see. It sees the load from the cold side plus the I²R losses. And so your thermal system, whatever that may be, as Sean mentioned, we're not trying to, obviously eliminate air cooling or liquid cooling, but whatever your thermal management system is, if you implement a thermoelectric cooler, it has to handle, the load that you're cooling plus the extra load that the thermoelectric device creates itself. So diving a little bit deeper into what things that can we change within the device in order to, kind of optimize its performance, whether you're trying to optimize for efficiency or for max cooling or max delta T. As I mentioned, because the Peltier effect is primarily driven by the material properties, and bismuth telluride is the main material that's used for these kind of application spaces. Most materials are very similar. There are different material manufacturing methods where you can improve the material property slightly. But generally speaking, most thermoelectric devices are going to be operating around the same performance metrics if they're using bismuth telluride materials. There's a few degrees here and there difference. But from the design standpoint, the other knobs we have are the geometric parameters of the elements inside. How many we put together in the structure and what that cross-sectional area and that element length are. And there are physical limitations currently with traditional thermoelectric materials in terms of how small we can scale these down or how large we can make them. But there is a wide array of possibilities that we can have in order to kind of optimize the design. And so generally speaking, if you're just looking at like a particular voltage that you want to operate at, you have a system where you can only operate at 3 volts or 12 volts. That's primarily driven by the number of junctions that you have in the system. So the V operating or the Vmax of the device is primarily driven by N, the number of elements that you have. When you're trying to, design for, high current or lower current applications, and usually, your system may be limited in power, or you may have a certain cooling that you want to achieve within the device structure. You limit the current by really changing the resistance of the device. And again, as I mentioned before, it's kind of this geometric parameter L over A, because the material property is fixed. And then you try to balance that out with the thermal conductance through it. So you have kind of competing parameters here in competing material properties. But generally speaking, for higher current, you want lower resistance, which meaning you have a lower L and you have higher A. And then for lower current, you typically have longer links and smaller cross-sectional area through the devices. And then for Qmax, like designing for just maximum cooling, you really just want to, move as much current through the device itself. You can kind of think of in a thermoelectric device, the current is the medium that moves the heat through it, similar to like a vapor compressor system where you have your refrigerant moving through the system. In a thermoelectric system, the voltage is kind of the pump, and the current is kind of the medium that's moving the heat through the system itself. So for higher Q, you typically need, larger cross-section area, smaller elements in terms of length, and, larger cross-section areas. And then for the maximum COP, in the condition where we're really trying to just maximize, for every watt you're putting into the TEC device, per watt of cooling that your system requires. If we understand the system and really understand all the system parameters, we can really design for that, what we call the current for maximum COP. In order to do that, we really need to know the operating voltage that we want to be operating at, the target delta T, because as I mentioned, the temperature difference, larger temperature difference usually will result in smaller COPs, and smaller temperature differences for higher COPs. But knowing that target delta T will help us then back out what the proper geometry is to solve for the current that will yield that maximum COP point. And those are some of the things that we do at Sheetak, our application team and our engineering team, to work with customers on their specific applications to optimize the solution for their system requirements. And just taking a look at just some typical thermoelectric devices out there in the market. The ones we've been talking about primarily are single stage devices. And when we mean single stage, it's one layer of elements. So you have two ceramics typically, and then one level of these, the junctions or the elements inside. And for a single stage device, typically the max delta T that you'll see in the market at a reference temperature of say 27 C is on the order of 75 degrees C. And really what that means is if you powered it fully to its maximum voltage and maximum current at Imax and at Vmax, you'll see the maximum temperature difference across the top and cold of 75. And that's under zero load. So it's not cooling anything, it's just what is the maximum temperature difference that you can create across the device. And there are certain applications where the load is not really like a high heat density load like we're talking about in this webinar. That could be very small powers, 100 milliwatts or just a watt or two, and you can really push that maximum temperature difference. But the most you're going to see is about 75. Multi-staging is adding different layers of elements across the the devices, and so you could go with 2 stages, 3 stages, or 4 stages. And the reason that you put the stages together are primarily just so that you can increase that delta T across the device. So whereas a single stage has 75 delta T max, a 2 stage may have 97, a 3 stage may have 100, 110. And the more stages you add, the more delta T, but the lower the cooling power that you get. There are different ways of doing the multi-staging. In some cases, you add an intermediate ceramic and add different stacks of elements. There's other ways like the Centum C3 product line where we eliminate the intermediate ceramic and this direct stack the elements on top of each other for kind of more compact sizes. So different ways of implementing the single and multi-stage. I'll touch briefly on thin film technology. This is an area where Sheetak continues to develop and research, and starting to kind of commercialize products out of this. This technology is different than the bulk traditional ones we've been talking about because they're thin film. They are more on the micron and nanoscale materials versus the kind of the millimeter scale elements we were just talking about. Still bismuth telluride based. They're based on a silicon substrate architecture. And you can think of the way that we make these as more like an additive process. The materials are deposited layer by layer until you end up with a final structure very similar to other integrated circuits and other silicon manufacturing processes. And at the end, we're left with a device architecture on wafer that we dice out and end up being fully functional devices. The advantages here is just really the mechanical, the sizes that can be achieved and the heat density, whereas the elements we were looking at before may be, half a millimeter or millimeter or so in physical dimensions. The thin film elements are, half a micron, something less than 10 microns in thickness, and the diameters or the X and Y dimensions are 30 microns, 40 microns, so much smaller element sizes. So you can end up with a very high couple density and a very high cooling density and very thin form factors, typically less than a half a millimeter. But very similar operating parameters and operating characteristics as traditional, other than just the scale and the ability to pack a lot of elements into a small area. And then we can also do different things with materials here because of the way that we're depositing the materials. We can add different dopants and such to try to tailor those material properties we talked about before to improve the Z value of the devices. So jumping into some actual applications related to data centers and the AI thermal challenges that Sean was mentioning, and what a lot of topics have been at the Thermal Live, as we talked about earlier. So one of the main areas that thermoelectrics are being used today and have been used in these optical transceiver cooling. And this is an area where we continue to push the limits of what we can do with traditional bulk devices. And they require small form factors and in order to fit into the packaging that's needed for these optical transceivers. So typically, on the right-hand side, you'll see like a TO can with a thermoelectric device mounted to the TO can, and the heat is dissipated through that. And then on the cold side or on the temperature control side is the laser diode, and sometimes there's a photodiode and some other components that makes up this system. And what's critical there is the temperature stability. And so the ability for the TC to maintain a very controlled temperature so that the wavelengths are controlled precisely as needed. And then with higher bandwidth and higher data transmission, of course, the heat starts to increase. And so being able to design devices and systems that have the optimal efficiency for a given application and meet the geometric form factor that's needed for the application is critical. And so often these TECs require leg geometries that are 0.2 or 0.3 or 0.4 millimeters in X and Y dimensions, and as thin as maybe 0.25, 0.3 up to say 0.5 or 0.6 in height. So very small leg geometries and typically lower couple counts, something like 8 couples, 12 couples, or 16 couples are operating at lower voltages, and the current can be tuned, as I mentioned before, to match the cooling power required for the application. If you design for maximum COP, as I mentioned before, there are gains that can be had, 20 to 30% improvement just versus say just taking an off-the-shelf TC and trying to force it into the application. So that's why kind of working with the application engineering and engineering team to really understand the requirements of the application so that we can really design and modify the chip to operate most efficiently. In emerging technology, just like the thin film being an emerging technology, is these co-packaged optic systems. So these are starting to become implemented, and I think will slowly, grow, as the market demands require. And in this case, instead of having individual, kind of transceivers, as we were kind of looking at before, you're wanting to pack the all the elements into one system. And of course, with packing everything together, things need to get smaller and miniaturized. And that's where, the thin film technology that we talked about earlier is a good solution for this type of implementation and co-packaging. With the bulk devices, it's very hard to scale down much below the sizes that I was just talking about. Something that's maybe 2 millimeters, 2 millimeters by 2 millimeters, or 5 by 5, or even down to 1 by 1 millimeters. Some of these laser diodes and such are a half a millimeter by half a millimeter, or 0.6 or so. And in order to scale down to that size, you really need some new technology or some change in the technology in order to address that. And that's where the thin film technology can kind of come into play. And we're currently working on these types of applications, as the technology develops and as these co-packaged optics evolve, to where we can directly integrate thin film thermoelectric elements directly below the diodes, so that they can individually control those and be part of the system. And then the larger system can be cooled, by your broader macro kind of thermal management system. But at the individual level, you can leverage the thin film technology to manage that heat. Now, looking at direct chip cooling, the TDPs that Sean mentioned, 400 watts going up to 1,000 watts, that's really not feasible for just a single TEC module to manage. The heat density is just too high, and as I mentioned, with this coefficient of performance, if you're really trying to drive 30 or 40 degrees temperature difference, directly at the chip with the Peltier cooler, the COPs will be below 1, and you'll be dissipating more heat than what you're cooling at a factor of 2 to 3x. And then, of course, your power requirements for your system go up. So we're not really arguing for direct to chip cooling for these high TDP AI chips. The COP and just the heat density is just not there at this point. Conventional TCs are more suited for 5, 15, 20 kind of watts per centimeter squared at an individual chip level. And so leveraging the advantages of the TEC in terms of its response time, kind of its geometric ability to scale down in thin form factors and integrate them into other components, is kind of the way that we're exploring and currently looking at for implementing traditional thermoelectric coolers directly coupled with some of the advanced liquid cooling systems that are being implemented into data center and AI chip cooling today. Historically, without liquid cooling, with just high performance air cooling and such, it was kind of limiting in what you could do in kind of these hybrid systems. But now with all of the direct to chip liquid cooling, whether it's water only or whether it's pump two-phase systems that are out there, the capacity of those systems in order to move the heat and to manage the heat at the local level is allowing and enabling other configurations where we can now leverage the parameters of the TEC in order to manage heat from other peripheral components. So as these AI chips and such get very hot, there's very local heat. So your VRM modules, your high band memory that's close to the modules will overheat, and sometimes they throttle back because they're limited in what they can be able to deliver to the demands of the AI chip itself. And so this is where the hybrid approach of putting a TEC chip in conjunction with a liquid cooling system, to where we locally control kind of these hot spots or these other modules around the system, to where we can enable the VRMs or the HBMs to keep up with the demands of the AI chip and maintain those temperatures within their operating parameters as needed. Another way that potentially TECs can be used in the AI chip applications, not so much maybe within the data center, but in the edge servers. Again, with edge AI chips maybe being on the order of 50 watts to 200 watts. That's within the heat density and the cooling range of an individual chip to be able to directly address the cooling density of those chips. So maybe in edge systems, edge servers, and edge AI chips, where maybe the environment is less controlled and you have larger temperature swings, that's where the advantages of the TEC being able to manage that heat and control the temperature down to the required operating temperature, and being able to cool even below ambient in some conditions as needed could be a potential way to implement those. Another way of looking at a TEC in these AI cooling systems, again, with the advent of direct-to-chip liquid cooling and existing cooling loops in data centers, a lot of times the systems are limited in being able to manage the peak power of the chips. And so you can design your thermal system to be able to manage the base load thermal requirements, and then leverage thermoelectric cooled liquid to liquid systems in order to handle the peak demand from the AI chips, and then also potentially store reservoirs of colder water in order to implement and push into the system as needed. So the advantages of the TEC system being able to cool below ambient temperatures and to respond, fast response times, enables them to be implemented and kind of work in conjunction with existing liquid cooling systems inside the data center. And the big push for data center cooling to go away from open loop systems and into closed loop chilled water systems completely contained within the data center environment is another potential application space where leveraging the advantages of the direct-to-chip liquid cooling that's available in the market today, and implementing a TEC-based system alongside of that to manage the peak demand, we can see potential TDP improvements of 20 to 40%, depending on kind of the system requirements and how it's implemented. So it's another way of thinking about how to potentially leverage kind of these emerging trends in the data center cooling market with liquid cooling and take advantages of the strengths of the TEC in terms of fast response times, compact form factors, precision cooling, and the ability to integrate directly with liquid to liquid systems is another way of kind of looking at these thermal challenges. And these are just different areas that we're working with customers to kind of implement TECs and face these AI challenges. And with that, I'll hand it over to Sean to talk about our products a little bit and then to wrap up.
Yeah, thanks, Brandon. Yeah, really good stuff. So, I think we proposed several thermal challenges and solutions that this technology can be leveraged for. We're working with customers today, sort of spanning our product portfolio down at the micro level. So micro centum is our smallest form factor sort of bulk style chip today, as small as 2-3 millimeters squared. So this is where you would see implementation in the pluggable or on top of that TO can that Brandon showed. A lot of our business is centered in this single and multi-stage architecture of the devices. So, depending on the delta T max that you guys are trying to achieve, we could leverage different types of products to meet your system requirements. And, even looking at deep cooling, delta T max is around 160 degrees C at a hot side temperature of 50 C. By stacking those thermoelectric levels on top of each other to achieve greater cooling capacity. So, beyond just the TEC portfolio, David, I see you had a question in the chat around thermoelectric generators. Yeah, so we also sell a complete portfolio of TEGs. So going back to Brandon's fire and ice slide on the generation mode, we do work with customers with our TEGs to to convert waste heat into usable energy. But really what we're doing is we're providing a custom solution for customers. So, it's not relatively an off-the-shelf product. While we can sell and provide, off-the-shelf product, where our value comes into play, as Brandon mentioned, is working with an applications engineer, working with the design team and designing a custom solution, whether it be at the micro scale or something bigger, 30, 40, 60, 100 millimeters in form factor size, depending on the application. And we can assist on the substrate side, custom substrates, custom finishes, custom designs. That's really where Sheetak prides itself. So I think with that, we could wrap up. If anybody has any questions about the company, about our products, let's continue this conversation. We'd love for you to follow along on our LinkedIn. We do produce a lot of really good content on this technology, whether it's white papers or blog articles specific to applications. We are dedicated to trying to build out a library for our engineering community around this technology to show how they can leverage it in their own systems. So thank you everybody for joining.
Awesome. Thanks, Brandon and Sean. After that, I feel like a bit of a thermoelectric expert. You guys did a great job explaining a lot of those concepts. And that is a good reminder that Sheetak has provided a link to their white paper, and it's called AI-Ready Thermoelectric Solutions for Data Center Thermal Management. You can access that as well as a copy of the presentation slides in the Docs tab. So we're gonna try to get to all these questions, but if we don't get to your question, just know that we're gonna forward these along to Sean and Brandon and their team afterwards, and somebody from Sheetak can follow up with you. You guys ready to jump into these?
Sure.
Great. First one says, what is the power headroom required for TEC technology compared to air or liquid cooling?
It kind of depends. As I mentioned before, really the main factor that drives the power in that COP, so how efficient you can leverage a TEC for cooling something, is what that delta T is. So if you're just leveraging a TEC, in some cases, say like 10 to 20 degrees of cooling, so maybe taking your air cooling system and you want to extend the limits of that, or taking a liquid cooling system and say pushing your case temperature down even further. If it's 10 to 20 degrees, your COP may be over 1. And so like if you're cooling, say 100 watts, maybe you're only putting in 50 watts or something of the TEC. If you're hovering right around that 1 point, it's 1 to 1. If you're cooling 100 watts, you're going to have to put 100 watts into the TEC. And if the system is designed maybe to try to maximize that temperature difference and maximize the cooling, the power requirements can be high. So if you get down into the COPs that are like a half, or down to 0.2 or so, if you're cooling 100 watts, you may have to put in 200 watts or 150 watts and such. So it really just depends on what you're trying to achieve with the TEC, and we can work with you on the different requirements in order to best analyze it and see if it makes sense or not.
Gotcha. Great. This is an interesting one, guys. Can this be used in laptop cooling, replacing fans? And what will be the cost considering mass production's volumes?
We'd have to kind of look at it and look at the specific requirements. I mean, the TEC, you can think of the TEC as like a mover of heat. I mentioned before, it's like a heat pump. So, and these devices are pretty thin, typically a couple of millimeters in thickness, but they still need to get that heat out somewhere into the ambient. So your laptop, you could potentially sync the hot side of the TEC to your back case of your laptop with some advanced spreading materials that maybe we have seen at Thermal Live this year and in past to kind of spread that heat over that large area and then leverage the laptop as kind of your heat sink. It's possible to do that, but a lot of times the challenge comes in to how effective that heat management is that's matched to that hot side. If it's not very effective, then it requires your TEC to generate larger temperature differences, which gets you into that wrong COP operating point. So then it may not make sense from a power perspective, but anything's feasible. And with some of the advanced materials that are out there today, we're always constantly taking a look at applications that maybe weren't possible 5-10 years ago, but they're possible now because of the other complementary products that are out there today.
Well, and as you guys were talking about, thinner, smaller, the idea that we're packing more and more and more into, even smaller sizes of, containers essentially for these devices. What y'all are making is getting better while getting smaller.
Mm-hmm.
Yes.
Amazing.
Yep.
Exactly. And we're trying to push the material side. It's been fairly stagnant and limited, and that's where the thin film technology comes into play, because we have more control on what we can do with the materials at the molecular level, for lack of a better word there, because we can kind of dope the materials differently. For the bismuth telluride, there's been some improvements over the years, but not substantial. More of the improvements have been on the manufacturing side, better quality, refinement of the material so you can get to smaller geometries and still be effective. But we're at Sheetak, we're kind of looking at both fronts, both the material side and the ability to miniaturize at both the bulk and the thin film level.
Great. We'll answer a few more here. Charles asks, are your materials crystalline or pressed and sintered?
Typically, we use the extruded material, so hot pressed or extruded materials, because those give better material properties, better Z properties that I mentioned before, and then also you get better mechanical strength. So in order to get to the geometries that I mentioned in the for the optical transceiver cooling, the leg geometries being maybe 0.3 by 0.3 millimeters and very thin, say a 0.5 millimeter or 0.6 or maybe 0.3, in order to hold the geometry and you don't have like chips outs and cracking and stuff, you need it to be very mechanically strong. And the only materials that will allow for that are kind of the extruded or the hot pressed material. The crystalline just won't allow you to get there. And usually one way to tell is looking at the delta T max of a TEC. So if you look at a data sheet and the delta T max only shows like 66, 67, 68 for a single stage, usually that means it's crystalline material. And if you're pushing into the low 70s, 72, 73, 74, usually that's an indication that it's extruded material. And then the small geometries is another indication that it's the hot pressed or extruded material.
Gotcha. Okay. Well, so the same person has a follow-up question. Since you mentioned delta T, what is the max delta T with the thin film devices?
It's a great question. Yeah. So, so ultimately, what we're trying to get to is on par with traditional bulk materials in terms of delta T max. Right now, we're not quite there. If a single stage bulk product can get to, like I mentioned before, 70 something, 73, 74, we're less than that currently. And part of that is just the challenges with the packaging. All these elements I mentioned are on the micron scale, and then some of the layers that we're putting in place are on the nano scale. And so there are parasitic losses and other things in the system that we're trying to optimize around to get to the theoretical maximum delta T we can get to. There's nothing in the physics currently that say that you can't get there, but the challenge is really implementing it at scale, and taking advantages of the miniaturization. So we're looking at the material properties and making making improvements there as we kind of improve the manufacturing processes. But even with that, let's say like the co-packaged optics example, you may not need a full 70 degrees temperature difference. You may only need a 10 or 15 degree temperature difference there. And in those cases, the other advantages of the thin film being that you can scale down to the physical size that's needed and implement it directly, and the fact that it's built on the silicon architecture, we feel like there's going to be some product adoption of the technology even before maybe we can get to the full 70 degrees delta T max, because the other advantages of the technology, along with the delta T that we can achieve, will enable it to be implemented. But ultimately, with the thin films, we think we could even get beyond kind of where the traditional materials are today as well, because we can dope the materials and improve the materials in the long term.
Great. All right. We're going to do 2 more questions. All right. I know we're a little bit over time, but it's a great conversation. So we will not overlap with the next session. This one asks, how do you manage control boards in data centers? Is it a dedicated board or is it integrated?
I think what you're asking here is like, how would you manage the control and the power to the TEC itself is the way I'm interpreting this question. And so that would be, it wouldn't be integrated into the TEC structure. It would be an external power and control that would go to the chip itself. A lot of times these control systems, there's off-the-shelf controllers that are available, IC controllers that would map and work in conjunction with your onboard power supplies and regulators that are there, and you'd have to add that in addition to what's existing in order to manage the power and the control to the TEC. TECs are typically controlled, with the PWM control. So like in order to manage the current going through it or the cooling power, you can control it with PWM or with just a DC current. They don't typically like to just be hard on or hard off. You can work them that way, but usually managing them with a DC current or with PWM is the most recommended way to manage the power to them.
Awesome. Okay, last question. And again, we'll forward these questions on to these guys after today. And so they'll follow up with you. But yeah, great questions, guys. Thank you, everybody. The last question, we talked a lot about data centers here. Are there any applications in industries across EV, IoT, aerospace, besides data centers that you discussed?
Yes. Do you want to answer that, Sean, or you want me to answer as I can answer it too? I don't want to take all the questions.
I mean, no, I'll just say absolutely. So, our customer base spans sort of aerospace, medical, automotive, so you name it. These devices have broad application. So simply, yes, Brandon could go into some specifics, but we're just focusing on data centers today because that's sort of a hot topic that everybody is concerned with. But I mean, we could give countless presentations on how people are adopting this technology, into wearables or into refrigeration systems or chillers, both at the sort of civilian and military scale. So absolutely.
Nice.
Yep.
All right. Well, thank you, guys. That's all the time we have for this session. So Brandon and Sean from Sheetak, thank you for your incredibly informative presentation and for taking our questions.
Thank you.
All right. Thank you, everyone. Enjoyed it.
Yeah. We're heading into our final session after this for Thermal Live Fall 2025. Our next presentation will begin in about 6 minutes, and we look forward to seeing you then.
All right. Thanks.